welcome to this problem walkthrough. Today, we'll explore an interesting and classic problem, largest rectangle in histogram. This problem is a great exercise in understanding how to use stacks and arrays to efficiently solve computational geometry challenges. Let's dive in and break it down step by step. In this problem, we are working with a histogram that is represented as an array of integers called heights. Each integer in the array corresponds to the height of a bar in the histogram, and all bars have a fixed width of 1. Our goal is to determine the area of the largest rectangle that can be formed using one or more contiguous bars in the histogram. For example, if the input array is 2, 1, 5, 6, 2, 3, our task is to calculate the maximum rectangular area that can be formed. The output will be a single integer that represents this area. Looking at the first example, when the input is heights equals 2, 1, 5, 6, 2, 3, the largest rectangle has a height of 5, which spans from index 2 to index 3. Since the rectangle spans 2 bars, its width is 2. Multiplying the height by the width, we get the area as 5 times 2, which equals 10. For the second example, with heights equals 2, 4, the largest rectangle is formed by the second bar, which has a height of 4 and a width of 1. This gives an area of 4 times 1, resulting in an output of 4. In the third example, if all the bars have a height of 0, such as heights equals 0, 0, 0, no rectangle can have a positive area, so the output is 0. The problem also has constraints to consider. The length of the heights array can be as large as 100,000, and each bar height can go up to 10,000. Additionally, we must handle edge cases, such as when there is only one bar, like heights equals 3, where the area would simply be 3. For arrays of all zeros, the output is always 0. In cases where the heights are increasing, such as 1, 2, 3, 4, 5, the largest rectangle forms using the last 3 bars, giving an area of 9. Similarly, for decreasing heights like 5, 4, 3, 2, 1, the largest rectangle also has an area of 9, formed by the first 3 bars. To start, let's consider the brute force approach. The intuition here is straightforward. For each bar in the histogram, we try to calculate the area of the largest rectangle that can be formed using that bar as the height. To do this, we expand outwards from the current bar, checking both to the left and the right, until we find the nearest bars that are shorter than the current one. These boundaries define the width of the rectangle, while the height remains the same as the current bar. The area is simply the product of the height and width. We repeat this process for every bar in the histogram, keeping track of the maximum area encountered. However, while this approach is simple to understand and implement, it is highly inefficient. For each bar, we perform a linear scan to find the boundaries, which leads to a time complexity of O(n) per bar. Since we repeat this for all bars, the overall time complexity becomes O(n) squared. On the plus side, the space complexity is O(1), as we don't use any additional data structures beyond basic variables. However, the brute force method has significant drawbacks, particularly its inefficiency with larger inputs due to its quadratic time complexity. To address this, we turn to an optimized approach that uses a monotonic stack. The key idea here is to efficiently find the nearest smaller bars to the left and right of each bar using a stack. This eliminates the need for redundant scans. The stack is maintained in such a way that it always stores indices of bars in increasing order of height. As we traverse the histogram, for each bar, we check whether its height is smaller than the height of the bar at the top of the stack. If it is, we pop indices from the stack and calculate the area of rectangles formed by the popped bars. The height of the rectangle is determined by the popped bar, while the width is calculated using the current index and the index of the bar now at the top of the stack. If the stack is empty, the width is simply the current index. This process ensures that each bar is pushed and popped from the stack only once, resulting in an overall time complexity of O(n). The stack itself requires O(n) space in the worst case, but this trade-off is well worth the performance improvement. The monotonic stack approach has several advantages. First, it is highly efficient and scales well for larger inputs, making it suitable for competitive programming scenarios. By leveraging the stack, we avoid redundant computations and reuse information we've already gathered, which leads to significant performance gains. This method is built on the key observation that the problem can be reduced to finding the nearest smaller bars for each bar in the histogram, and a stack is an ideal tool for solving this subproblem efficiently. For these reasons, the monotonic stack approach is the preferred strategy. While it does require additional space compared to the brute force method, the trade-off is acceptable given the dramatic improvement in time complexity. The breakthrough insight here is recognizing that we don't need to calculate the area for every possible rectangle. Instead, the stack inherently tracks the critical indices we need to compute the largest rectangle in constant time for each bar. To summarize, there are a few key observations that make the optimized approach so effective. First, the largest rectangle that can be formed using a given bar is determined by the nearest smaller bars on its left and right. Second, using a monotonic stack is an efficient way to track these boundaries and retrieve them as needed. By focusing on these boundaries and the heights of the bars, we eliminate the need to calculate areas for all possible rectangles. This reduces the time complexity of the solution from O(n)² in the brute force approach to O(n) in the stack-based approach. The trade-offs are clear. While the brute force method is simpler to implement, it is impractical for larger inputs due to its inefficiency. On the other hand, the monotonic stack approach requires a slightly more complex implementation and additional space, but it delivers optimal performance. For competitive programming and other scenarios where scalability is crucial, the monotonic stack approach is undoubtedly the better choice. In this problem, we are given a histogram represented as an array of integers, where each value corresponds to the height of a bar and the width of each bar is 1. Our goal is to find the area of the largest rectangle that can be formed within the histogram. To begin, we can explore a brute force approach. First, we iterate through each bar in the histogram, treating the current bar as the potential height of our rectangle. From this bar, we expand outwards in both directions to determine the rectangle's boundaries. To expand to the left, we continue moving leftward until we reach a bar shorter than the current one or the start of the histogram. Similarly, we expand to the right until we encounter a shorter bar or the end of the histogram. These boundaries will help us define the extent of the rectangle centered around the current bar. Once we have determined the left and right boundaries for the current bar, we calculate the area of the rectangle. The width of the rectangle is derived from the difference between the right and left boundaries, plus 1 to include the current bar. Multiplying this width by the height of the current bar gives us the area. We then compare this area with the maximum area found so far and update the maximum if the new area is larger. This process is repeated for every bar in the histogram, ensuring that all possible rectangles are considered. Finally, after iterating through all bars, we return the maximum area as the result. While this approach is straightforward and guarantees correctness, it involves scanning outward from each bar, making it computationally expensive for large histograms. The brute force solution works by calculating the area for every possible rectangle in the histogram, treating each bar as the height and expanding outward to determine boundaries. While this method is easy to understand, it is inefficient due to its nested loops. Specifically, the time complexity is O(n)², where n is the number of bars, because for each bar, the algorithm may need to scan the entire histogram to calculate boundaries. Regarding data structures, we use a simple array to store the histogram and a few variables to track the expanding boundaries and the maximum area. This lack of additional data structures makes the approach straightforward, but the inefficiency in handling larger datasets is a significant drawback. Despite being intuitive, the brute force approach has clear limitations. Its O(n)² time complexity makes it impractical for larger histograms, and it involves redundant calculations, as many boundary expansions overlap across iterations. To optimize this, a stack-based approach can be used to reduce the complexity to O(n). This method efficiently calculates boundaries for all bars in a single pass and avoids redundant computations by pre-computing the nearest smaller bars on the left and right for each bar. Additionally, we must consider edge cases, such as an empty histogram where the maximum area is 0, or a single bar where the area equals the bar's height. For histograms with equal height bars, the rectangle spans the entire width, while for strictly increasing or decreasing heights, the algorithm still works by expanding boundaries until smaller bars are encountered. These optimizations and considerations make the problem both challenging and interesting to solve efficiently. The provided Python implementation solves the largest rectangle in histogram problem using a stack-based approach. Here's a detailed breakdown of the code. 1. Initialization. The stack is used to store indices of the histogram bars, helping track taller bars as we iterate. The max_area variable tracks the largest rectangle area found so far. The length of the input, n, is calculated for convenience. 2. Iterating through the bars. The loop iterates over each index I in the histogram. For each bar, a while loop checks if the stack is non-empty and if the current bar height I is smaller than the height of the bar at the index stored at the stack's top. This ensures that we calculate areas for all taller bars that cannot extend further due to the current shorter bar. Inside the while loop, the top index is popped from the stack, and the rectangle's height is determined using heights, stack.pop. The width is calculated as I if the stack is empty, indicating the rectangle spans from the start, or as I stack-1, 1 otherwise. The rectangle area is then calculated as height*width, and max_area is updated if this area is larger than the previous maximum. After processing, the current index I is pushed onto the stack. 3. Processing remaining bars. Once the loop completes, there may still be indices left in the stack. These represent bars that could extend to the end of the histogram. For each remaining bar, the height is determined as before, and the width is calculated as n, entire width of the histogram, if the stack is empty, or n is stack-1, 1 otherwise. The area is calculated and max_area is updated if needed. 4. Return the result. After processing all bars in the stack, the largest rectangle area is stored in max_area, which is returned as the result. This approach officially calculates the largest rectangle in O(n) time, as each index is pushed and popped from the stack at most once. It handles edge cases like an empty histogram or when all bars are of equal height effectively. This is the Java implementation of LeetCode problem number 84, largest rectangle in histogram. The logic mirrors the Python solution, utilizing a stack to maintain indices of histogram bars. Key differences include Java's type declarations, use of the stack class, and handling of stack operations. The algorithm efficiently calculates the largest rectangle area in O(n) time by iterating through the histogram and processing remaining elements in the stack. To solve this problem, we use a stack-based approach to track the indices of the histogram bars. Starting with an empty stack and a variable max_area initialized to 0, we iterate through the heights array. At index 0, the height is 2, so we push the index 0 onto the stack. Moving to index 1, the height is 1, which is less than the height at the top of the stack, 2. This triggers a calculation where we pop the index 0 from the stack, use the height 2, and calculate the width as 1, resulting in an area of 2. We update max_area to 2 and then push index 1 onto the stack. As we continue, at index 2 the height is 5, which is greater than the height at the top of the stack, so we push index 2 onto the stack. Similarly, at index 3, the height is 6, so we push index 3. When we reach index 4, the height is 2, which is less than the height at the top of the stack, 6. This triggers a series of calculations. We pop index 3, calculate an area of 6, then pop index 2, calculate an area of 10, and update max_area to 10. Finally, we push index 4 onto the stack. At index 5, the height is 3, which is again greater than the height at the top of the stack, so we push it. After completing the iteration, we process the remaining indices in the stack, calculating areas for heights 3, 2, and 1, but none exceed the current max_area of 10. The final result is 10. Now let's analyze a case with increasing heights, where the input is 1, 2, 3, 4, 5. Starting with an empty stack and max_area set to 0, we iterate through the array. At index 0, the height is 1, so we push index 0 onto the stack. At index 1, the height is 2, which is greater than the height at the top of the stack, so we push index 1. Similarly, at indices 2, 3, and 4, the heights are 3, 4, and 5 respectively, and since each is greater than the previous, we push their indices onto the stack. Once the iteration is complete, we process the stack. Starting from index 4, we calculate areas using the heights and their respective widths. For height 5 the area is 5, for height 4 the area is 8, for height 3 the area is 9, for height 2 the area is 8, and for height 1 the area is 5. The maximum area encountered is 9, so the final output is 9. This example demonstrates that when heights are in increasing order, all calculations are deferred until the end, and the maximum area typically comes from a wider rectangle formed using earlier heights. Finally, we examine a case where all heights are equal, with the input 5, 5, 5, 5. We initialize the stack and max_area as before and begin iterating through the heights. At each index, the height is 5, so we push the indices 0, 1, 2, and 3 onto the stack sequentially. After completing the iteration, we process the stack. Starting with index 3, we calculate areas using the height 5 and the respective widths. For index 3 the width is 1, giving an area of 5, for index 2 the width is 2, giving an area of 10, for index 1 the width is 3, giving an area of 15, and for index 0 the width is 4, giving an area of 20. The maximum area encountered is 20. This example shows that when all heights are the same, the largest rectangle spans the entire width of the histogram, resulting in the maximum area being the product of the height and the total width of the array. Here, we analyze the time and space complexity of our solution. The time complexity is O(n), where n represents the number of bars in the histogram. This is because the algorithm makes a single pass through the array using a loop that iterates n times. Each bar is pushed onto the stack exactly once and popped from the stack at most once. Since pushing and popping from the stack are constant time operations, the total time for all stack operations also amounts to O(n). Additionally, within the while loop, when a bar is popped, we calculate the width and area in constant time, meaning these operations don't add any extra overhead. Combining the linear traversal and the stack operations, we see that the overall time complexity remains O(n). As for space complexity, the solution uses a stack to store the indices of histogram bars. In the worst-case scenario, such as when the heights are sorted in increasing order, all n bars will be pushed onto the stack, resulting in O(n) space usage. The other variables, like max_area, height, and width, only require constant space, so the total space complexity is dominated by the stack, making it O(n) in the worst case. Now, let's break this down into best, average, and worst-case scenarios. In the best case, when the histogram bars are sorted in increasing order, each bar is pushed onto the stack once and popped only at the very end, resulting in O(n) time complexity. On average, the algorithm processes each bar in constant time for both push and pop operations, so the time complexity remains O(n). In the worst case, where the histogram bars are sorted in decreasing order, each bar is pushed and popped individually. Even in this scenario, the stack operations still take O(n) time in total. Comparing this to the naive approach, which involves examining all possible rectangles formed by every pair of bars using two nested loops, the brute force method has a time complexity of O(n²). Since each rectangle's area is computed in constant time, the total complexity for the brute force approach is O(n²). In contrast, our optimized stack-based approach avoids redundant computations, efficiently calculating the maximum area in a single pass and reducing the time complexity to O(n). This efficiency is achieved by leveraging the stack to track indices and process each bar only once. To further solidify our understanding, let's provide a mathematical proof for the big O time complexity. Consider n, the number of bars in the histogram. Each bar is pushed onto the stack once, which gives us a total of O(n) pushes. Similarly, each bar is popped from the stack once, resulting in O(n) total pops. The operations performed inside the while loop, such as calculating width and area, are constant time operations, or O(1). Combining these, the total number of operations is proportional to 2n plus some constant c, where c accounts for the constant time operations. When we ignore constants and lower order terms, the overall time complexity simplifies to O(n). This mathematical breakdown reaffirms that our algorithm is highly efficient, processing the histogram in linear time. When solving the largest rectangle in a histogram problem, there are several common mistakes to watch out for. First, edge cases are often overlooked. Examples include histograms where all bar heights are 0 or scenarios with just a single bar. These edge cases can lead to incorrect results if not explicitly tested. Another frequent issue is mishandling boundary conditions. For instance, when expanding left and right to find the nearest smaller bars, it's easy to inadvertently go out of bounds. Proper boundary checks are essential to avoid runtime errors. In optimized solutions that utilize a stack, errors such as forgetting to pop elements or mismanaging indices can result in infinite loops or incorrect area calculations. Carefully tracing stack operations during debugging can help prevent these problems. Additionally, while brute force methods might seem intuitive, their O(n)² time complexity makes them impractical for large inputs. Unless the problem explicitly requires you to demonstrate this approach, it's best to avoid it. Finally, in languages like C++, ignoring the risk of integer overflow can lead to incorrect area computations. Always use appropriate data types, especially when dealing with large heights, to ensure calculations remain accurate. Now, let's focus on key insights for interviews. The stack-based optimization is the most efficient solution for this problem, with a time complexity of O(n). Interviewers often expect you to be proficient with this approach, so it's crucial to not only implement it but also understand and articulate why it works. For instance, you should explain how the stack helps efficiently track the nearest smaller heights for each bar. Additionally, pre-computing arrays for the left and right bounds of each bar is an alternative approach. While it's easier to implement, it requires additional space, so understanding when and why to use this method is important. Be prepared to discuss the trade-offs between brute force and optimal solutions, particularly in terms of time and space complexity. Interviewers may also appreciate hearing about real-world applications of this problem, such as skyline problems, stock spans, or other scenarios involving height-based challenges. Demonstrating this kind of practical understanding can set you apart. This problem is closely related to others that you might encounter during interviews. For example, LeetCode 42, Trapping Rainwater, involves a similar use of a monotonic stack to calculate water trapped between bars. Of course, LeetCode 84, the largest rectangle in a histogram, is the direct problem we're discussing, and it's a very common interview question. Another related problem, LeetCode 85, Maximal Rectangle, builds on this concept by extending it to a two-dimensional matrix. Finally, LeetCode 907, Sum of Subarray Minimums, leverages a monotonic stack to track the nearest smaller elements in a different context. Beyond related problems, it's worth considering alternative approaches to solving this one. The brute force method, for instance, involves calculating the area for every possible rectangle. While this approach has O(n)² time complexity and O(1) space complexity, it's only practical for small inputs or as a way to build intuition for the problem. The stack-based approach is the optimal solution for this problem. It uses a monotonic stack to efficiently find the nearest smaller bars on the left and right for each bar. This method has a time complexity of O(n) and a space complexity of O(n), making it the preferred choice for large inputs. Another viable strategy involves pre-computing arrays for the nearest smaller elements on both sides of each bar. While this approach is easier to implement, it requires additional space and achieves the same time complexity of O(n). A less common but conceptually interesting method is divide and conquer. This approach recursively divides the histogram into smaller sections, calculating the largest rectangle within each. However, its time complexity of O(n) log n and space complexity of O log n, due to the recursion stack, make it less practical in most scenarios. Despite its limitations, it's worth discussing in theoretical settings to demonstrate your depth of understanding. Great job following along. In this session, we tackled the largest rectangle in histogram problem and learned how to optimize our solution using a stack-based approach. Remember, mastering these concepts can make a big difference in your coding interviews. Thanks for watching, and don't forget to subscribe for more problem-solving tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!